Okay, this lecture here is about something called force oscillation. Okay, first we need to describe something called compare free and force oscillation. A system that the oscillating system that we have been studying so far are called free oscillations and free oscillations with damping. Right? So what happens is that when we say some oscillation is free means there are no external periodic driving force. The keyword here is periodic. Periodic means that the force is oscillating also, has a frequency. Okay, so far the examples we look at, the oscillating system has got some external force acting on it, but the forces acting on them on the oscillator are not periodic. Okay, so the system oscillates at its own natural frequency. The natural frequency is determined by usually the parameter, like in the case of a pendulum, it's the length of the pendulum and the value of g. Like we saw this equation in the previous lecture here. So this is very much determined by the L, the length of pendulum in g, and it is every pendulum. It doesn't matter what mesh you put. If you use the same length, you put on the same place, same G, you will have the same frequency. This is called the natural frequency. So every system that has some elastic property will be able to oscillate with naturally with this frequency. Okay, so even a tall building, for example, a tall building can have a natural frequency as well. This is a very tall building, 50-story tall building, for example. Um, when if a strong wind or earth were to oscillate, then this building is able to oscillate sideways. Similarly, very large structures like bridge and all that also has a natural frequency, right until very small scale like molecular level also has natural frequency. Okay, so things that can oscillate without external periodic driving force, they are still to be able to oscillate freely or having free oscillations. Okay, so what about force oscillations? Force oscillation will be oscillation that happens when you apply an external periodic driving force. The keyword here is external periodic driving force. So this external periodic driving force will supply energy, will try to supply energy to the oscillating system continuously, keep on supplying energy. So because of this periodic driving force, external force, the periodic driving force has its own frequency. This is the frequency of the external driving force. And because it is trying to force the system to oscillate, the oscillator will therefore vibrate or oscillate with the same frequency as the frequency of the force. Okay, so if the force is vibrating very fast, the oscillator will try to vibrate very fast because it's the force that is trying to provide the energy. Okay, so the oscillator will try to follow the oscillation of the external driving frequency. It's no longer following it's no longer oscillating on its own because of the external force. The external force disturb it, try to provide energy. It will tend to oscillate with the frequency of the external force. Okay, so you follow the oscillation of the external driving force. Okay, so let's look at this gentleman here oscillating, trying to oscillate pendulum. On the left hand side, we have this. Um, his hand is not moving. His hand holding the pendulum not moving. So on the left, we have free oscillation. On the right, you can see that he is swinging his hand that is holding the pendulum. So he's providing a frequency, and then if the frequency is matching, you can actually swing it to a very large amplitude. Okay, right. So compare the two. The left hand side is free oscillation without providing an external driving frequency. On the right hand side, you have the force oscillation where the hand is providing the driving force at a certain frequency. Okay. Now, because of this ability to provide energy from an external force, the amplitude of vibration will also change. Now, if you provide the frequency, uh, the external force, if you provide a frequency that is different from the natural frequency, then the amplitude is usually very small. Okay, so imagine if you're holding a pendulum and the pendulum is able to oscillate at, let's say, 10 hertz, and if you're vibrating at 2 hertz, it's not going to increase its amplitude very much. Or if the natural frequency is 10 hertz and you're trying to oscillate at 100 hertz, then it's not going to able to provide energy that is in sync with the natural frequency. Okay, but if the natural frequency is about the same as the frequency of the driving force, then something happens. The amplitude is going to swing to a very, very large value. Okay, so if you look at the previous video here, okay, the video on the right hand side here, you see the hand is swinging the same rate as a natural frequency. So because of that, it's able to provide a very large amplitude to the swing. Okay, when that happens, we say that resonance has occurred. When that happens, when the frequency of oscillation become very large, when the frequency of the uh, driving force is almost equal to the natural frequency system, this oscillation is said to be having resonance. Okay, the amplitude um, of oscillation become a maximum, become very, very large. Okay, so what happens is during at resonance, when the external frequency, when I say external frequency, means the frequency of the external force is equal to the natural frequency of system, there is a maximum rate of energy transfer from the force to the oscillator. Okay, so that's why the amplitude because you keep on providing energy, the amplitude will become larger and larger and larger. Okay, so if there is no damping force, this amplitude can swing until it's so large that it can break the system. Okay, so but usually there's some kind of damping force that takes away some of the energy, so it will try to limit the amplitude so that it doesn't become very big, right? So other examples, like you sit on a swing here, so on the right hand side you will sit on a swing. If somebody were to push you at the same frequency as the frequency of the swing, at the right time when you're going away, you give you a push, right, and give you a push, so you'll be able to achieve a large amplitude oscillation. But if you're pushing very fast, most of the time, if you're pushing, your hands are pushing very fast, but there's nothing for you to push, then of course the amplitude would not be very large. Or if your frequency of pushing is very low, when the person comes back to you, you do not push, then of course the swing doesn't gain amplitude as well. And same thing on the left hand side, we have a pump. We have a pump that pushes the mesh, the red color mesh that is attached to a spring here. So if the frequency is matching, it's able to supply the energy and causes the amplitude oscillation to become larger and larger and larger. Okay, so this is what we call resonance. Okay, when the natural frequency of the system equals to the frequency of the external force that is driving it. Okay, so if so the amplitude of vibration will be maximum at resonance. That means when the natural frequency equals to the frequency of the external force. And however, the magnitude, the amplitude also depends on the degree of damping. Okay, so because damping, if you remember, is a kind of resistive force that takes away the energy from the system to the surrounding. So when you have the higher damping, you expect more energy to be taken away. So you expect the amplitude, even the resonance, to be lower than compared to the case when there is lesser damping, right? So if there is no damping, then of course the system will, will oscillate with infinitely large amplitude. Okay, so let's look at the kind of graph that that can be plotted. So this is called resonance graph, where we plot an amplitude variation, how the amplitude of the oscillating changes when we have different frequency of the external force. So this is the driving frequency, or the frequency of the external force. Okay, so we change it from very low value to a very large value, and in the case of no damping, ideally if there's no damping, this amplitude at resonance can go to infinity. The amplitude can actually go up to infinity. The F0 stands for, this F0 here stands for the natural frequency. So when the external frequency is increased up to the natural frequency here, shown by this vertical line, when the two matches here, the amplitude can go up to infinitely large in an ideal situation. It's like you keep on pouring energy into the oscillating system. No energy is taken out. You keep on adding energy to it. Of course, the amplitude is going to increase and increase until in a very, very large amplitude. Okay, so usually for such ideal case, we draw a dotted line all the way up and without closing the two curve. Okay, so this is to show an ideal case. But in real life, of course, there will be some kind of damping force that will limit the amplitude. So in real life, there will be some kind of damping that takes away some of the energy so that the amplitude doesn't go to infinity. So there will be some peak here, right? This peak that happens around the natural frequency. So F0, this is the natural frequency of the system. Um, when there was no external driving force, the natural frequency. And if you increase the damping further, you expect the if you increase the damping further, you expect the resistance, the damping force to take away more energy. Therefore, the maximum value of the amplitude, even near resonance, will become lower. Okay, the curve become less sharp now. So the peak will left or will decrease, and not just decrease, the frequency where the peak happens will also become lower. So you shift towards the left to a lower frequency. So this frequency here, the peak shift towards the left, right? It shift towards the left hand side, lower frequency, right? So it doesn't occur. It doesn't occur at the same. Um, the peak doesn't occur at the natural frequency. If it occur at the lower than at the frequency that is lower than the natural frequency when the damping become higher and higher. Okay, right. There's another thing you need to take note of for different degrees of damping. So this is light damping, this will be heavier damping. Okay, this will be heavy damping. So for different degrees of damping, you'll find that the different curve they do not cross. All the curves do not cross each other. Yeah, right? They don't cross each other. They get lower and lower. And also another thing is at the at the graph where f is zero. F0 means no external frequency. The frequency of the external force is zero. It means there is effectively don't have forced vibration. So all the graphs should be at the same point. They should start at the same point. They should have the same amplitude when there's no external driving frequency. The frequency, the f is zero. So this is the general shape of the graph for different degrees of damping for resonance. Okay. Right, if you look at example 18 here, you are given a series of graph and you're given line X is the one that is having resonance, but amplitude or oscillation varies with the frequency, right? So the driving oscillator has a constant amplitude at all frequencies. Okay, now which dashed line shows the response under condition when there's less damping? Less damping means that you expect the graph to be higher than x. Okay, the peak should be higher than x. So you look at all the graph. Of course, uh, D cannot be. D cannot be because it's lower. Okay, C also cannot be because C is higher. Okay, and no, some part is higher, some part is lower. So C cannot be. Now look at possible answer should be A or B. Okay, either A or B. But the problem with that doesn't cross with the line X. It's either A or B. But why is it B and not A? Because this one is the graph should meet at the same point. Okay, remember at f equals 0, they should have the same amplitude. So D is also wrong because D is also wrong. So the correct answer should be B. Where it doesn't cross the curve. The correct curve is higher than X in terms of its amplitude, maximum amplitude, and it doesn't cross X, and it starts at the same point or same amplitude when the external frequency is equal to 0. Okay, right. And in the lab, we can illustrate this resonance behavior by constructing something called Barton's pendulum. So what happens is we have a piece of string on the top here, and we tie a heavy pendulum on the right hand side. So this heavy pendulum, when it starts swinging, is able to transfer its energy through the string on top here. So it's going to vibrate this string here, and energy is transferred from the top string to the rest, because when it start oscillating, it's able to transfer energy to all the rest of the strings and start oscillating the other pendulum. Okay, so the one that oscillates with the largest amplitude will be one that has the same natural frequency, as the driving. This is a driving frequency. If you remember, the frequency of the period of oscillation is 2 pi square root L over G. Okay, so the frequency is 1 over T, so is 1 over 2 pi square root of G over L. So it depends only on the L. So this this driving pendulum has a length of L. So the one that is closest to it, pendulum C, has the same length L. So this two has the same length, therefore same frequency. Then therefore you expect C, after a while C will oscillate with a very, very large amplitude oscillation. Okay, let's look at this example here. This is how it's being set up. Okay, this guy, okay, is setting it up now. So the heavy pendulum is the one that's providing the force. Okay, it's transferring energy to all the other pendulum. Okay, you wait a while, you will see that. Okay, the cup deck has the same length, has the same natural frequency, has the same frequency as a driving pendulum, will oscillate with the largest amplitude. Okay, okay, let's move on. Right, example 19. This is about the graph that shows. You're asked to pick which diagram that um, show the correct answer for resonance. So example 19, we have two bodies P and Q that have a given initial displacement and then release. So you compare these two oscillators. Obviously, they have more or less the same frequency. If you compare the time taken here, uh, okay, the time here is about the same. This T here is about the same as here. Okay, they have the same frequency, and then apart from that, the Q also has a higher damping. Okay, heavy damping, higher uh, damping force. Therefore, when you pick the resonance curve, the answer should be that Q should have a lower amplitude. When you plot the resonance curve, when you pick the resonance curve, how the amplitude varies with the frequency when P and Q are subjected to external driving force. So when you draw the resonance curve, you expect P to have a higher peak because P has a lower damping compared to Q. So Q has a higher damping, so its peak is lower, and then um, it is the peak of Q also shift a little bit towards the left. Okay, right. Resonance in real life has got some useful applications apart from having fun in the playground. Um, uh, the principal resonance is used for tuning of musical instruments, right? You take a tuning fork of a certain frequency, and then you put near the instrument and you sound them together. You are able to cause vibration with a larger amplitude. Okay, when the natural frequency of the string or the instrument matches the frequency of the tuning fork, for example. It's not just in mechanical vibration, in electronic circuit, for example, the tuning of radio station. When you tune to a radio station, for example, you're actually trying to change the frequency of your oscillator circuit in your radio to match the frequency of the station they are tuning in. So the station is broadcast at say 95 megahertz. You're tuning the radio frequency, your circuit there, you change it to 95 megahertz so that you can pick up the signal from the air. You can resonate and therefore pick up the energy from the um, of the wave that's in it. Um, Resonance is also used in the principle of operation of microwave oven. Microwave ovens, they use microwave that has a frequency which is very similar to the natural frequency of oscillation of water molecules. So you put some food inside, some food with water molecules inside. Um, if you turn on the put in the microwave oven and turn on the microwave is going to set up resonant vibration of the water molecules, and this oscillation generates heat to cook the food. Okay, but if you put other things that doesn't have water inside, it's not going to generate oscillation and therefore produce heat. Um, Resonance also is occurs at the very much small subatomic level. Like in the case of nuclear magnetic resonance imaging, is actually used to as a diagnostic imaging device to look at study the brain cells, for example. Um, it's actually resonance at a molecular level, at the subatomic level, actually. So this is resonance happening at a very, very, very tiny scale. Okay, so resonance happens at very large scale and very big, very small scale. Can be mechanical in nature, can be electronic or molecular in nature as well. So there are many, many different possibilities of resonance. Okay, so let's look at one possible destructive nature of resonance. Uh, in the case of a bridge, for example, if the construction of bridge is not proper, if it built in such a way that at a place, for example, where it happened to match the natural frequency of the wind that's blowing at a certain rate, certain frequency, then it can cause destruction to the bridge, for example. In other situations, for example, earthquakes, they're actually generating a lot of ground vibrations, and those vibrations, if they happen to match the natural frequency of building, can actually cause greater destruction. So some buildings that are close to the epicenter of the earthquake actually do not suffer much damage compared to buildings that are actually further away from epicenter, because the wave that carries, the earthquake frequency that propagates from the epicenter actually happen to match that natural frequency of the buildings that are actually further away, and actually can cause more damage. Okay, so let's look at a situation here in in the 40s, where this bridge that was constructed in the US called the Tacoma Narrows Bridge, and it was a newly built bridge that was open for a few months. Okay. Okay, so you you can actually set up you can actually, under the right condition, you can actually set up some, an amplifier with a microphone. For example, you sing with the correct high high pitched sound. If that frequency of your singing can actually match the frequency of oscillation of a wine glass, you can actually cause it to break into pieces. The vibration of the sound can actually shatter the wine glass. Okay, you can take a look at this video here. I will not show you because it's quite long here, but these are possibilities. Okay, right. So we'll end this lecture here for now. Right. Thank you very much.